I'm your host today, Joe Jasinski. Heather is also one of our other board members. We have two great talks planned for tonight. But before we get started, I'm going to just talk a little bit about, first of all, we have a code of conduct, which, is pretty standard stuff. Just be respectful to each other. Maybe, yeah. So just be respectful to each other, and we should be good. Let's see. ChiPy is not possible without the help of a bunch of board members. So we have 6 board members right now. I'm looking for a 7th if anyone's interested in volunteering. And perfect. I'll just use, great. Also, if you are just want to help out in any way, we need help for our website, for various events, and for getting kind of our special interest groups kicked off again after COVID. There's still ones that are active, so please get involved. Let's see, next slide. So, for example, we've had in the past, we've had various different initiatives, like the mentorship program, the AlgoSig. The AlgoSig is actually pretty active. Python lunch break, where we meet during lunch. The project night and the web guild, and so any of these things need volunteers to help boot them up again. And but we're really excited to be back doing live meetings as much as we can. We've got a bunch of sponsors who help us with this. Next slide. We thank all of our sponsors for supporting ChiPy. There's a lot of costs involved in this. And in particular, our host, and tonight, our host is Coyote Logistics, which we'll be hearing from them in just a minute. So. Thank you very much for all that. And so we got 2 great talks tonight. We're also live streaming this, so we'll have a break in between the 2 talks as we get kind of set up. Are we actually live? Yes, we're live. Good. So without further ado, let's bring Anna onto the stream, and we can start with her talk. Let's see. 1 second while I get set up here. Let's see. Try going to one of these here. You can remove that one. Can you hear us, Anna?
Yep. Perfectly.
This is a first for us, where we're doing a hybrid online live stream and in-person meeting. So we're working out the technical issues here. So, all right.
Ooh, what was the sound?
Can you hear us now?
Yes.
We'll just have to have that extra box included. All right, go for it when you're ready.
Yeah, awesome. Hi, everyone. I'm Anna Story, a software engineer. This year, I'm back to academia, back to teaching, and just started my first semester at the College of the Holy Cross in Worcester, Massachusetts. But previously, I worked for Decathlon, and before that, Amazon, for the Alexa AI org for a few years there. And today I'm going to present my lightning talk on optimizing Python code and helpful tips and tricks for faster code. So, what is actually fast code? So there are three aspects, three axes along which we can measure our code. There's time, CPU consumption, and memory consumption. And there's a great deal of libraries and modules in Python that help you measure those. I'll just list a few here, some of them maybe the most popular, the mostly used. So for time, there are time and timeit modules. And I'll insert here a quick caveat saying that measuring time is a little tricky with computers. There is a great read, quite well known, falsehoods programmers believe about time that I'm linking here. So feel free to check it out on your free time. But nonetheless, it's an accepted benchmark, and I'm also going to be using it for some of my examples. For CPU, there is C profile, for example, and for memory, memory profiler. I also have a Medium post on profiling in Python, where I provide a few more details about each one of them, what kind of input they take, what kind of output they provide, some differences, for instance, between the time and timeit modules. So feel free to check it out. I'm providing the link at the bottom of this slide as well. So say you're working on your first big data or data science project, and you realize that your code is literally hitting the wall. You're sort of wondering, what can you do? Can you speed it up a little bit, at least a little bit? Can you do anything about it? And the great thing is that, yes, you can. There's a myriad of things that you can do, starting from kind of more straightforward tweaks to your code that you can add here and there, all the way to more sophisticated and generalized approaches and frameworks that you can utilize. And I'm going to talk about them more towards the end of my talk. So starting from the simpler things, what can you do? The first thing, the go-to thing is to think about, are there any loops that you could replace with least comprehension in Python? So what does least comprehension bring? So if I take kind of a simplistic example, for instance, here I have this dummy function that squares integers using a for loop. All it does, it declares the squared list output they're going to return in the end, and then iterate over a range of integers within a limit, and appends the square of each integer to the output list. So if I run it on my machine, here is a sample code for calling the timeit module and printing its output to standard output. I get 9.3 blah 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 seconds. What if I want to make it faster with least comprehension? Here I have a new function that achieves the exact same thing using least comprehension. And when I run timeit on it and print the output, I get a little over 6 seconds. So if you think in relative terms, it's a great improvement. And especially so if you think about real world amounts of data that you might have as input, they will significantly improve the performance of your program. Can we do better? Actually, we can. So sometimes it's a great idea to think about, are there any places where you can avoid unnecessary for loops and least comprehensions altogether? And one of the examples I can think of is a pattern that sometimes shows up in my day-to-day life, my day-to-day work. And also, I see that quite often in lead code kind of coding problems, where you know that you're going to be returning an output array containing some computation for each element of input list, for instance. So here I'm giving an example that is very close to my language processing, machine learning kind of domain example. So say I have a list of rows textual data, and I want to compute something, number of tokens, words per row. Um, so the shortcut is to use the default value, for instance, 0, and multiply it by the length of the input list. And the output would look as the bottom line on this screenshot. So this way you avoid iteration altogether. What other things can help speed up your code? Another area that I would definitely recommend explore more and pay more attention to is Python built-ins. So what are the kind of things that I'm talking about is those are all sorts of functions, starting from very simple things like sum, max, map, filter, reduce, etc. To some others like the join method in the string module and the item getter in the operator module. So what benefits do they bring? For instance, especially if you're starting out in programming, you may be kind of tempted to write some of that code, some of that logic by yourself, maybe map or reduce kind of logic, because you can. But the interesting thing is that these kind of things are already implemented in Python, and they're most probably implemented very efficiently. They may be implemented in C under the hood, and so they will do those things probably a lot faster than the kind of code that I would have written from scratch by myself. Another example I can think of is also a pattern that shows up very often in my work, and that I also see a lot in this kind of lead code coding problems, where you may have an input string, and you're asked to reduce this string in some particular way to hash it or something like that. And you may want, starting out, you may want to just keep augmenting the output string character by character. But a more efficient way is to add, to append, more precisely, every computation step to an output list, and then call the strings join method on this output list. Why? Because strings are immutable. So if you're building a string character by character, Python will store every version of this intermediate version of the string, so to speak, behind the scenes, and that'll use up a lot of memory, and consequently, your program will become slower and slower. So that's one of the examples where that comes in super handy. And another example that I can think of the top of my head is, say you have an input list of tuples, for instance, users' first name, last name, and you want to sort them based on their last name. So the default sorting would would sort them by the first names, but for our purposes, you can use operators item getter as the key for the sorted function, and you can see at the bottom line the output they will get. And the built-in function will do it faster and more efficiently. Once again, than kind of code that I would have maybe written myself sort of quickly on the go. Okay. What other things can we do to improve the runtime of our code? Sometimes you might want to start thinking about larger questions, not just these little tweaks here and there. For example, if you're working with objects, you might want to objects and their attributes. Depending on the logic of your code, you might want to assign some of the attributes to local variables. For example, a very typical example is, say I have an object rectangle and I have its height and width. So here you can see in the screenshot, I'm assigning the height attribute to rectangle underscore height and the width to rectangle underscore width. And somewhere below in the code, not too far away, I'm computing the surface using those local variables. And just, a few lines later, perimeter and maybe something else. So what is the benefit of this? Although it might not, this particular method might not shave off a lot of time during the execution of your code, to put it concisely, the trick is that if you're not using the local variables, Python first has to retrieve the self object and then its attributes. Whereas when you use the local variables, it skips one step, and so makes it a little faster. And the general recommendation along those lines would be explore and know your data structures and objects that you're using, know them well, and choose approaches wisely. What kind of things do I mean here? For instance, if you're working with Python dictionaries, at least in Python 3, if you want to retrieve a key or check for a key in the dictionary, Python allows for two types of syntax to do that. Here you can see the top and the bottom one. They both work. However, if you experiment and try it out, the top one, without the explicitly calling the keys method, will run faster. So again, depending on the logic of your code, what you're trying to achieve, you're not reusing the list of the keys. Go for a faster, simpler version of the syntax that Python allows. Another example that I would cite here is the question, the dilemma of list versus set. So that's something that I've seen numerous times, witnessed some other people hesitate about. Definitely has popped up as a question for myself as well. Say you're working with data, you have, which happens very often in Python, you have a list of data items that you're going to process. And then you stop for a moment and think, well, if I need to retrieve an element, and I know that if I retrieve an element from a set that's going to be a one, it's super efficient and super tempting to do. Why don't I do that here? On the other hand, again, depending on the logic of your code, if I realize that actually I'm only going to be retrieving one element, for instance, or once, what will actually happen behind the scenes? Again, in order for those all of those elements of my input list to be added to the set, I'll have to iterate through all of those elements in the list, and that'll create extra overhead that actually I don't need. So probably not going to use, not going to cast my list to a set in that situation. So the general recommendation is to really think carefully about the structures, the behavior, and what approach to choose. Okay, but what happens if you've tried all those things? You've replaced your loops with list comprehensions wherever you could, but it doesn't really help that much. So that might be the time for more serious solutions. And what kind of things would I recommend there? So in case you're just starting out maybe in data science and you're not super familiar with the following libraries, they definitely should be on your radar. So the kind of libraries I'm talking about are, for instance, NumPy or Pandas. NumPy is a library for basically numeric computation in Python, and it uses its own data structure, NumPy arrays, that are a lot faster and they're more compact than the standard Python lists. I'm not going to go into a lot of detail how they implement it here because of the scope of the lightning talk, but it's a super interesting topic. It's open information. You can find it on the web and read about it. It's really interesting. But here I'm citing just a little bit of short explanation of how that helps to optimize your code, taken from the NumPy documentation, official documentation. Another library is Pandas, that is quite popular. It's quite mature, and even though some of the default data structures in Pandas that allow you to process data are not designed to be efficient. There are so many ways to scale it to big data sets and fine-tune its performance that it's even provided in its official documentation. And again, I'm providing a link here for anyone who's interested to check it out. What other things might be helpful? Another big topic is what we generally mean by the concept of concurrency, maybe more specifically concurrency and parallelism. So in Python, there are three maybe major libraries to achieve those kind of results: threading, async IO, and multiprocessing. And again, I'm not going to go into a lot of detail here in terms of its differences, but I have another Medium post on both the concepts of concurrency and parallelism and all those three libraries. And I'm providing the link here. And I'm also giving their examples how to use them and then what kind of use cases, which one is best to use. And the last thing I would mention here is just-in-time or JIT compilers. So JIT compilers use information about your data structures, data types in your code, and create specialized machine code, which helps your program run faster. And you will see the real benefit of that if you're applying it to larger programs that are run frequently. So if it's a one-off kind of script for a quick pipeline, that you're not going to see real benefit there. But for larger, frequently used programs in your code, that might be a way to go. And a couple of examples I cite here are the JIT compiler provided with ChiPy, which is a Python implementation of Python. And here again, I'm adding a few short sentences describing its benefits. Again, relying on the official documentation. So they claim to speed up the code around 3 times compared to CPython 2.7 implementation. And the other one is Numbo, which is sort of standalone JIT compiler that also claims to speed up the code in order of 2 orders of magnitude. So yeah, here are all the tips and tricks I wanted to share with you today. Thank you for your attention, and I'm happy to take any questions.
Let's give it a round of applause. So does anyone have any questions?
I do.
Here, one second.
Hey, I'm way off camera here, but hey, for the JIT that PY does, PyPy or whatever, does it compile when you run, or does it actually watch your loops to find out where it should compile and optimize like the Java JIT does? And then if it's waiting until you have several iterations in runtime to get the performance, do you need to run, maybe warm up if you are doing a transaction processing thing where you want to send some dummy transactions through to warm it up like some low latency applications do with Java?
Yeah, that's a great question. I'm trying to remember because I haven't used it myself for a bit of time now. I'm trying to remember nuts and bolts of the PyPy's JIT compiler. I wouldn't want to pull things out of thin air and sort of maybe misinform you. I would refer to documentation or maybe even trying out things. Yeah, especially if you're interested in sort of in comparison with Java's JIT compiler.
I have a quick question. Do you have any strategies or techniques for optimizing parallel or concurrent programs?
Yeah, that's a good question. So as I mentioned in the slides, I actually have a whole post on concurrent and parallel code. So feel free to check that out. But it's a great topic on its own. There's so much to weed out first before providing a specific suggestion, right? So depending on first, is your code more IO dependent, or is it heavier on the CPU consumption, and so on. And all the way to more practical questions, because it may be very easy to give a suggestion, so to speak, abstractly. Go for this, use that's a great library. But then anyone who's worked with threading, for instance, will say, yes, that may be a great tool, but if I'm solving a very specific problem, when I have such and such requirements in my whole development cycle, is it something I would really want to go for, right? Because it may be working with code that uses threading, maybe, to put it nicely, a little bit more complicated, especially if you have a team maybe composed of more junior engineers. The time they would spend weeding out every time you need to debug something, maybe the time that this will consume will actually kill all of the benefit of using such a wonderful library. But yeah, if you want to check out some examples, feel free to refer to the post that I'm linking there.
I'll be sure to check that post out. Does anyone else have any questions?
Hi, I have a question about your presentation. Can I ask you to go back to your built-in functions slide?
Yep.
So could you elaborate on their specific example where you use the sorted method? Why would you use one in brackets? What does it do specifically in this example?
Yeah, sure. So here, if I were to call the sorted function on my tuples list as is, it would return the output of, sorry, let me sort it in my head. So it's going to be Abby Smith, Adam Johnson, right? Jane Addams. So sorting by the first element lexicographically, right? However, if I want them to be sorted by the last names, for instance, um, so the one in the parentheses here for the item getter specifies the index of the element in the tuples that I want to be used for sorting. And so here, if you look at the output, the example output, so the last names, oops, sorry, the last names are sorted, are used for sorting. So it's Adams and then Johnson and then Smith. Does it make sense?
It does, but why does every, the tuple Abby Smith goes all the way to the end? So why does it switch from the first position to the last position?
Right, because Smith starts with S, right, which is the lowest in the lexicographical sorting.
Oh, okay, makes sense. All right, thank you.
Yeah.
Any other questions? Go one back there.
So it's just very quick on the same one. What I would go for with this key is lambda x colon x of 1. Are you saying that it's more performant to do this item getter from the operator library than use a lambda function in the key? The lambda key?
Oh, I love this question. I wouldn't know the speed of either of the top of my head. That's something that I would experiment if I was curious to see. I would experiment, using maybe like the time it modules and see which one runs faster on larger input data.
Absolutely. Thank you.
Anyone else? All right, let's give Anna another round of applause. Thank you very much for staying in the room and giving me more talk. So,
Thank you, everyone.
I'd like to introduce our sponsor here, Coyote Logistics, and Nick Petrovitz, and he'll talk a little bit about the space.
Hey everyone, thanks for coming. My voice is shot, unfortunately, so I'll try the best I can to say hello to everyone. But hi, I'm Nick Petrovitz, VP of Data Strategy and Engineering here at Coyote. We use Python a lot for all of our data science and data engineering tasks and MLOps, et cetera. I'm really glad to have you all here tonight, and I hope we can use the space again to host another event. And hopefully I can give another talk sometime here in the future. My voice will not be completely shot, and I won't be stringed here to talk to all of you. But thanks for coming. Plenty of pizza and beer, cold brew, some soda and stuff too. So enjoy. Thanks.
We'll take a few minute break before we start our next talk. So stick with us.
Hey folks, so there's 3 books here that if you're interested in browsing, feel free. My name is written in them. If you happen to walk away with them, which I hope you don't, you can get in touch with me and return them. I say this having managed a little library at great personal risk. But yeah, I'm excited to speak to you all soon.
The worst time about how to not use for loops.
Yeah.
right? Okay. But it's kind of about putting that picture together like a big map, and that's the goal. That's what I want you to take away from it. You should be able to be like, oh yeah, I recommend a system, whatever, that does this and then that, and I could write it if I needed to. So the most abstract system is kind of like, it's just like an advertising problem, right? There's this big like hoarding, there's a big billboard, and somehow you have to get stuff on it, and you know that people are going to see it, and then you hope that they'll engage with it. So you have a bunch of items, and there could be all sorts of things. You could have like any number of like specific items that are all houses, or you could be like Facebook Marketplace, which has everything. And now this is the key part. You want like a magic wand or like a wise elder or some type of machine learning pipeline to do something to these items and give you kind of a really logical yes, no to whether that should be shown on the billboard or not, right? And of course, this engine, this wise elder, whoever it is going to need data to learn from, even if it's like a human being that you're like, what should we recommend? You're going to need to give it data. And then in the middle, there's like a bunch of the futzy stuff, which is most of my job as a machine learning engineer. Sorry to break it to you. But all of the last mile stuff is the bulk of what I actually do. Design, UI, coordinating with like creative if you're like, oh, how should this look when we actually show it on the page? The logistics of like, well, how do I know when you need a recommendation to be served and how do I make sure that it's ready for you? And all of the operations involved with all of that. And then you actually get like this pretty thing on the hoarding, which is like, ooh, personalized for you, or like a personalized playlist, or Amazon trying to push you the same thing that you already bought, even though you already bought it, which is like a bug in the system. And then they show you something at the end of it, right? So it's really maybe looking already a bit like a production line. And that's, I'm going to be using that a lot. But before that, site, like we zoom out even one more time. And think about it from a couple of different angles because of, again, the fact that recommender systems are, they're like inherently social. They're like quite complicated. You can't just be like, oh, this is just like a data production line, because they're affecting people and you're trying to infer things about what people like and how they behave. So there's economics. So you can think of it as you have like a marketplace of users and items, which is why recommender systems become like something you see on any site that has a massive catalog. Spotify, Amazon, like Facebook, like anything that has so many items that you cannot possibly look through them all yourself has a recommender system. And so you assume that users are going to have preferences for some of these items, but you also assume that they simply do not have the time to kind of go out there and discover all of them themselves, right? So your system can help them out. Recommenders decrease friction in the marketplace, and they make it easier to connect users and items that are a good fit. And so a frictionless marketplace has usually more transactions, more exchanges, and usually if you own the platform, that's good for you, right? The next way to think about it is something we already touched on, which is advertising, where you have like this billboard, right? But the advertising problem, again, becomes kind of interesting because you're trying to connect users with items that they like that they probably wouldn't have found on their own, which is the whole thesis of like what an ad is. But the point is you only have this little snapshot to show them, and you hope that they like that. So it's really kind of like this partial information problem in an interesting way that has constraints too. So you have an advertising budget, you have to spend in risk, infrastructure, time and money whenever you want to go and put something on the billboard. And you have to think about what you're really risking. Like what if you recommend something that is one of the worst things on the site? You're going to actually take a hit from that, right? And so you think about also the surface areas, like on most types of sites, you would have like a home page, a discover page, or other like carousels or surface areas on the site that is the real estate, the hoardings, or the ad time that you buy. And then the goal, of course, is that advertising should grow the site and improve the user experience. And again, drilling back, recommender systems effectively serve like this self-running marketer that is always making little decisions about what's good and what should be shown to whom. And one more way is pattern recognition, which is where the whole machine learning thing comes in, so we don't have to talk about it for too long. This is not a machine learning talk. So we have past data on user item engagement. There's patterns in that data. We need an algorithm or a wise elder to crunch the data and use the patterns and to output sensible recommendations. And we can't really assume that a pattern exists. We actually need to test it by showing recommendations generated by some assumptions to users and seeing whether they're garbage or not. Now, sometimes you can do this by just kind of simulating and being like, well, if I saw this, would it look like garbage or not? But as you scale, as there's more risk, you might really want to think about placing actual human beings who are not part of your process in front of those recommendations to make sure that they're good, right? And finally, there's data pipelines, which is, again, like inherently linked with like all of this Python stuff, like NumPy, Pandas, and stuff like that. It's not enough to kind of just build a model, because you need all of the things that feed it to be like high quality. It's like installing like a jacuzzi when you have like, when you live in Flint, Michigan or something. It just doesn't make sense, because the raw material is not of the quality that you're kind of expecting when you put all of this like fancy like end pipelines on it, right? So what you really need is like for there to be like this robust set of data pipelines that feed into your machine learning, which might mean that if you're thinking about hiring a machine learning engineer, you should wait for like a year or something and build those pipelines and then do that. So you want to have scheduled or on-demand jobs that are crunching data, cleaning it up, and then the last mile that these machine learning engineers are going to build is to produce the recommendations. So that leads us to kind of two patterns of how you can design data pipelines for recommendations. One is recommendations at rest. I like to think of it as when you pre-compute recommendations, you store them in a database, and so they're just sitting there, they're at rest. And then when you need them, you kind of like query them out and you serve them. And then the other one is obviously a little bit more complicated. There's more moving parts, but the possibilities are endless because, like, you know, TikTok or whatever. You compute and serve recommendations on demand. You're like, okay, you're online, you're giving us this engagement data, crunch it into a model. Let's see who else is online. Bam, like we computed it right now and gave you these like recommendations, and you're gonna keep scrolling and scrolling and scrolling, which is, I'm sure, great for like profit and all of that stuff. So anyway, we come back now to formulating the recommendations problem after thinking about it like super abstractly. There is like a fairly simple mathematical formulation that's useful to have in your mind. So there's gonna be n users. They're gonna go ui through un, m items, vj, v1 through vm. And then for each of those, there's kind of a score, and you have a good guess as to what this score is for a large enough sample. The score is just the expected engagement between user I and item j. So there's as many scores as kind of the number of items and the number of users in a big ass matrix. Excuse my French. So if we have engagement data for some of these users and items, then you have basically millions of hypotheses, millions of models that you can train to kind of learn what is this mapping of score based on training data. And you can kind of guess this for any user item. And each of your models will kind of make different assumptions that they use, or different heuristics or different hypotheses that they internally use to arrive at this best guess. So you effectively have like a bunch of wise elders who can be like, I think I looked at all of the facts and it looks like this user will like these items. And then you could have another algorithm that's tweaked differently and has like a slightly different opinion or a completely different opinion. And so you start to think of like this set of recommenders that are like all going to have like different strengths. Like maybe some of them like are good at certain genres. Maybe some of them are good at like, I don't know, like really, general. Like maybe some of them just spit out the most popular and they're kind of like redundant or defunct. But you effectively like just reduce everything to a problem of predicting scores, and you have all of your engagement signals already. If you're keeping track of any of your data, you're already keeping track of that. So let's just like kind of quantify this in terms of like now a streaming site problem. So think of like thousands of homepage clicks every minute, like people just kind of like bored. And then a lot of monthly active users, about 1 million, like maybe some of them are logged in, maybe some of them are just kind of like browsing or whatever. But like, let's say like 1 million is the assumption for the users that you have like mappable data for. So these are the logged in ones. And you're not counting ones who are not logged in, so you can't really map their data as well. You have about 100,000 available items, like which is effectively just the people who are kind of online at any point in the month. But you can't actually show people who are available at any point in the month. You can only recommend people who are available right now. So that's kind of a constraint because at any moment, maybe like only 5 or 10,000 of these people are actually streaming. And so it's pointless if you say, hey, you want to click on this stream? And then someone goes there and they're not online, right? So Yeah, and the engagement metrics that you have from the past that you hopefully have been keeping track of, or you've invested in all of these data pipelines to keep track of them. You have clear information on like kind of what people are watching, what they're liking, whom they're messaging, and you can kind of just attach like very high trust numbers to these things based on your SQL analyses and things like that. And so talking a little bit more about now the architecture, this part might get a little bit dry, bear with me, but it's kind of useful to, again, flesh out as a diagram or an architecture. So we're going to have recommendations at rest. We're going to have a scheduled compute job to pre-compute and store recs in a database. We're going to do this like 4, 5, 6 times per day so that you kind of address something called the cold start problem a little more easily the more frequently you run your pipeline, because it means that if you run every 4 hours, then someone who logged onto your site 1 day ago will still actually see fresh recommendations, which is hard to guarantee in other situations. Then you have like a serving application that retrieves recommendations from the database on demand and serves it to like a downstream app that deals with the stuff of like attaching a pretty picture to it and the rating and like, giving a link to the page and all of that stuff. And then you have like a bunch of data sources that you're training on. This is like the meat of the machine learning, which is again 3 lines of code. Most of it is all of the pipes and all of that other stuff. But like we use watch data and we use just the last 1 month's watch data. Ideally, you would have like data analysts or other people who have a good eye on your business and a good intuition for it, again, vetting your assumptions about these things, because you just like give a data person free rein, they're just going to be like, yeah, whatever, I just assumed things. You need to kind of like go and tie that back into like people who have observed the operations and have a sense of like, is this a realistic average amount of minutes that people are watching, or is something completely screwed up? And then you move on to like other engagement signals like likes and messages. And again, now you have like these models that can be tweaked in how you set them up, but also they can be trained on different sources of data. So you're really adding like lots of perspectives to the room of potential recommenders in some sense. And then you can use other sources like hashtags and chats and stuff like that. This starts to go more into what is thought of as content-based recommendations. Everything that I talked about so far is completely agnostic of anything distinguishing about the item. Like it's just like, oh, users like items, so which other items would users like? And everything is treated in terms of indices. There's nothing that says, oh, this is like actually a user that belongs to this genre or that has this hashtag or something. So again, you open a whole new world of possibilities as you start tapping into more data sources. You can use more complicated models and things like that. Exciting work for machine learning engineers, but a lot of work too. And then the model logic that we're currently using is actually extremely simple. Like I said, it is just collaborative filtering. The model doesn't know anything distinguishing about users or items. It's just like en masse what patterns can we sense. Like maybe if you liked users number 2, 3, and 4, you would probably like user number 5. It's a bad way of explaining it, but kind of stupidly what is happening. And then in the future, again, we could move to content-based features and things like that. This is how much data our pipeline is currently using. We have like about 3 million users and 170,000 items, and I'm constantly every day just like churning all of those numbers and spitting it out. So this is a diagram of the architecture of how this is implemented. I think we can be pretty quick about going through it. Where's my mouse gone? Okay, there it is. So let's trace a request that comes from the user on like beyond the site app, right? Like this comes from a user who's outside of any of our infrastructure. They click on the home page and we get a request. I call this the web server, which is kind of like on the web team, which is different from the data team, which is what I'm on. So it's kind of a useful distinction because this is responsible for all of the like software engineering and like kind of like front end of this recommender system, right? Like I'm building only the machine learning pipeline that spits out the answer. So they deal with all of that, but then their system sends a little request to my Flask app here that is deployed on the cloud. The Flask app goes and retrieves stuff out of Redis, which is the database that we use where recommendations are stored. And so that goes all the way back. It's packaged into a pretty JSON. And then the web server, again, knows what to do with that and formats it in a pretty way so that the user sees what's up and has like a nice set of things to click on. And then on the other side, we have like kind of a slightly separate architecture, which Design-wise, it's important to like think about how much these are coupled, because you're both these systems are writing and reading to this shared database here. So there's like a little bit of tricky stuff going on there. But you basically pull your data, your training data out of like Snowflake or wherever you have it. You put that into like this daily job that is like just crunching the numbers and spitting out the recommendations. And then interestingly, because we have so many users, we actually have to compute, like the part that runs the model can run on one machine, but then the part that writes those recommendations for like millions of users has to be distributed. So again, you could have like kind of different needs based on different use cases in this whole situation. Okay, let's talk a little bit more about the Rex on REST versus Rex on demand paradigms. What we talked about so far was recommendations at rest, because they're just kind of shoved into this database that runs 4 times a day, and then you're just like, you close your eyes and you trust what's in the database. You can implement health checks, like have like metadata in the database that says these recommendations were generated at this time, and then when you're serving them out, be like, were they generated less than 1 day ago? And kind of like implement those types of checks, which is always a good practice. But all of that is kind of extra and you know, maintaining the system rather than building it. So let's talk about the difference between these two now, though. So the way that you should read this diagram is look at this whole marketplace of items, which has all of the items that are currently available, which go from like number 1 to number 10,000. And then this is the recommendations at rest pipeline, which has already stored like watch database recommendations or message database recommendations, these different flavors of recommenders like I talked about. And those are saying, okay, for a certain user, we have number 1, 9, 12, and 20, or like 520, 150K, 400K, not necessarily everything that is overlapping in what's available right now. And then you kind of intersect that at serve time. You get a request and you say, okay, I know what I have saved, I know what's available, I intersect them, and that's what I give you. You can think of maybe some obvious downsides to this, like what if nobody that you had saved is online right now? Oops, well then that user doesn't see recommendations. So that's not a good thing. But there's lots of kind of interesting heuristics you can use to expand this problem. Like you can have like what is called item similarity. So instead of just looking at the user item affinity, you now say, oh, which items are similar to which other items. And if you keep an index of that, then at any point you have like maybe like 2,000 similar items to this one person. And if they're not available, you could just see if any of the other 2,000 are available and maybe serve those up instead. So there's kind of like interesting little tricks and heuristics that you can use there to expand the pool. But that leads to like kind of the next paradigm, which is what you would want to build if you were kind of, you know, gearing in this direction, which is, well, can we just like keep a list of all of the live items, everything that's available right now, and just like kind of compute on demand which of those should be ranked and shown to the user, right? And so that is the Rex on demand paradigm, or recommendations live paradigm, where you kind of now start to have to maintain features. So you need to have, again, your data pipelines, your data scientists need to have like kind of reached a stage where you're like, okay, like this is like a list of features that we really trust. They might be generated by machine learning, or they might be like raw counts of things, like one feature, just like number of messages this user sent in the last 6 months or whatever. And you kind of like have all of those features, and now you have machine learning models that are able to like get those features and crunch them live. So they're pre-trained, they just have the parameters and the weights and the shape and the configuration. You just load them up with the data, crunch the data, and spit out the answer, all on demand. So the site sends a request, our servers take that request, they go get the features, put it through a model, crunch the numbers, get the recommendations, and then serve those recommendations back. There's no retrieval of the answer. There's kind of retrieval of the features that are used to compute the answer. And so it's obviously a lot more moving parts. Like the system I described previously, recommendations at rest, we were able to deploy kind of like mostly relying on Docker without worrying too much about Kubernetes or like, you know, a bunch of like kind of like microservices. Something like recommendations live, you would really need like literally like a supply chain of like hands constantly being like, oops, we need this feature, oops, we need this computation, and kind of like really throw that out to a bunch of Kubernetes jobs. Starts to seem like way more easy to manage that type of system. So it's again an interesting exercise in like when like tools outgrow the complexity of what they were suited to. Okay, so yeah, next we're gonna talk really quick about experiments. So one cool thing that we're able to do here, and that is generally a really good investment for any data team, is to think about ways in which you can start testing these hypotheses about which recommender or which model is good, right? Like you don't want to assume this because you're going to be wrong. Like it's a bunch of weights on a silicon chip. We cannot claim to have intuition about it. So what we really need to do is go and put it in front of someone and ask them and kind of like get surveys and run experiments on whether these things are good or bad. And in order to do this, I guess the easy part is just to like kind of like split things out and be like, oh, this week we tried this or that week we tried that. But what you really want to be able to do is place those things in comparison to each other through experiments. And that leads us kind of to experimental platforms that are nicely baked into the scope of this whole design we talked about. So say now, instead of kind of running the same job for all of your users, you split your users into 3 groups: control, variant 1, variant 2. And now you run separate jobs on data pulled for each of these users. And there's various ways where you have to kind of like disentangle how you're, splitting them up and things like that for your machine learning model to have, equal visibility on everybody. But effectively, this is very easy to do. You just kind of say, look, like train on the data, but now spit out recommendations of this type for this group and that type for that group. And now you kind of just have like this little arrow that you've sent through the system that identifies the source of those recommendations. And you can, assuming you have the right traceability, you just have to build one extra connection that allows kind of this serve infrastructure. You see the gap here in the colored lines. So blue goes all the way down here into Redis. Redis stores the information and knows that it came from a certain type of generation. You just have to build a little arrow through here, through the serving infrastructure, to now tell the stuff that you were already logging, this one extra piece of information, like where did I come from? And now you can kind of trace the effects of these different sources or your different experiments on the exact same metrics that you were looking at before, right? So then at the end, you end up having this nice report where maybe before you were like, oh, what happens if we put the button here or there? And you already built the pipeline to be like, well, now we know what happens if we put the button here or there. You use the same thing, but just for what the recommendations were made from, right? Or the logic that kind of underlay them. So yeah, that's effectively how you should think about building an experimental platform into the exact same architecture. I'm going to talk real quick about our stack, which is 90% Python. So on the compute side, again, you have to have this process that like computes stuff, takes in the data, and then gets recommendations for these users and then stores them in your storage, which is Redis. The code for that is almost entirely Python. We use pandas, PyRedis, ChiPy, scikit-learn, and then like Snowflake and the Redis Python package for kind of the interfacing. Dagster, which is a cool Airflow alternative, if you heard about it, but it's kind of a slightly different design paradigm, which I like. And we've been using that, Dagster, for orchestration. This is effectively just how you stitch your code together into something that is a little easier to cron and that is easier to log and kind of be like, they even have like a cool cloud now, so you could just like monitor your runs without necessarily having to like log into your machine and things like that. And then PyTest for testing. And then we also have like a bunch of like shell cron type of scripts that are for deployment, testing, or like health checks. Like I said, you want to have Redis kind of maintain a list of who's live right now, but then you need a job that's going to keep updating it with who's live right now. And then you need to make sure that that job doesn't fail. So it's kind of like a cron on a cron, keeping eyes on a cron, and then you kind of are like with the Spider-Man meme, everybody just making sure that things are okay. And then yeah, so the hardware that we're running on is just kind of all on the cloud. So we have like 60. The whole compute side runs on one massive VM. Again, we didn't have to think about Kubernetes because the problem was kind of constrained to like this static thing at rest. That will not suffice when we're moving to kind of like more dynamic computations. So that's 800 gigs of RAM, 3 million users, 300,000 items. So it's like a lot of matrices that it has to like crunch and like store in memory and like a bunch of write jobs. So it really is quite an intensive computation. Not to dissuade anybody though, like this is for like 3 million users. If you wanted to build like a prototype for like 100 users, you could easily do it in Google's free tier. So yeah, let that not be the credit card fears not be a limiting factor. And then on the other side, we have the serve infrastructure. So this is the stuff that gets HTTP requests for recommendations, pulls them out of Redis, and then serves them to a downstream app that like pretties them up and puts them on a page. And the code for that is, again, all Python. It's a Flask app. Literally, it's just like URL, like user ID, and then just recommendations. And then we have like a bunch of like URL params that are like, filtered down, or like region. Or another cool thing about the URL params is that like you can now have your downstream app kind of like force certain behaviors. Like, they can say, oh, we tried already to get the latest recommender model, so can you just give, but that sucks, so can you give us the default? And maybe they have their own downstream logic. You kind of like allow for more control and different levels of filters and logic on what is actually being shown to the user, because different teams often have like kind of different insights and things to contribute about that stuff. And then again, we use the Redis Python package on serve side because it has to only retrieve out. We may think about kind of like logging serve time things in Redis in the future, but again, so many open design questions, so many kind of constraints that it's just an interesting problem. And PyTest for testing, and what we run our hardware on is kind of auto-scaling Cloud Run virtual machines. So they auto-scale between 10 and 100 CPUs depending on the load, and there's a Dockerized deployment, so it just kind of like keeps cloning the container and spinning more up if there's demand. And we've been seeing a good amount of reliability with this. Like we are currently serving like a small fraction of load because we're still testing, but like maybe about 5 requests per second. And it's doing pretty well. It scales pretty well. This is all on Google Cloud, of course. Are they sponsors here? I don't know. Okay, so just to talk now about, like we said experiments, but like what is an experiment? How do you like design one? Like what does that even mean, right? Like there's so many things that could be tested, from like moving a button to like a machine learning assumption. Like it starts to get murky. So we can unpack that a little bit more. Like there's like clear levels for assumptions actually. One is just like what data are you using? You could just change that and have everything else be the same, and kind of like say, again, we have like an engagement score that could be watch data, likes, messages, whatever. You could like shape it differently. You could weigh it differently. You could say, exponentially weigh it for recency, or you could have another model that's like, maybe we should weigh things the most that were 3 months ago, and maybe that'll be like a nostalgia thing. I don't know, right? Like you could do anything. It could suck. That's what you need to accept. And then your compute side hypotheses could be like, what will the model do, right? Like, is it going to be a candidate generator? Is it going to rescore things? Like you might want models that maybe are designed to like flag offensive content or kind of like keep the space clean. And then you might want like kind of a downstream thing that is like just classifying whether something is offensive or not, oftentimes on a site. And then that gets like a little penalty that is like an independent referee from the first thing. Even if it gave it a really high score, you're like, whoops, looks offensive, maybe we reconsider. And again, you kind of have to think of the social logics of a recommender system and all sorts of other crazy stuff when you realize what this is doing to like an ecosystem or an economy or a marketplace. And then you can try other things like just other model shapes, like other math, and just throw it at the thing and see what it does. Singular value decomposition, alternating least squares. There's just a bunch of other acronyms that are not important. You can tune hyperparameters. And then this is cool, I think. This is interesting to me, which is the serve side or policy layer. I think I touched a little bit on it, but oftentimes some of the highest lift that you can get is not by letting like a machine learning engineer or data scientist just like run amok and be like, oh, maybe the dimensionality should go from 10 or to 20. But it's really kind of just asking your analyst, like, can you answer this question that helps me figure out what people are doing on this platform, right? And can we make something that we have inferred about their behavior easier or a better experience? Like, really simple here is just like exclude poor items. Like when you have like a billboard, like, I don't know, if Amazon had like the top spots be like the worst rated things, that would be a bad idea. But not every site has like that clear signal of like, this is a bad item, right? So you need to make sure that you're not accidentally putting kind of like lower quality things on your site up there, because that kind of ruins your reputation. People are like, wait, what? That's what it looks like now? Maybe this is not the place to be. And so heuristics for quality control that are at the same time not exclusive or not too simplistic. And that's an open-ended question. Again, you need to kind of try things, but also like evaluate them at the same time. And it's hard, but it's important. And then you need heuristics for kind of matching user preferences. For instance, like there's like oftentimes like genres or niches in marketplaces that you can figure out, but how much are you going to figure them out without being like too prescriptive or without like now starting to affect the dynamics of your site? Like if you saw the book there about Zuck, which is about Facebook, then that's like kind of a runaway train that maybe didn't go in the best direction. And then you have UI UX level interventions, like what should your surface areas look like? And this is where like your front-end engineers, your like product managers, your design thinkers, your creatives, your color scheme, all of that comes into the picture. And again, this whole thing should kind of illustrate again why it's important to keep your hypotheses super simple, because if you change too much at the same time, it's all garbage. Like you can't infer anything. And so there needs to be like good communication across the various teams that might be changing things, that might be testing things. You can't have someone move a button and you move the recommendations at the same time, and then you're just trying to figure out what the hell happened. And then of course, what new surface areas could you imagine? Like, I feel like Spotify is a great example of this. They have carousels that are literally like just machine learning models that have now been given names that are people now call like the blush playlist. What is Blush? It's like an algorithm. It's crunching the numbers every day and it's looking at what you liked and it's putting some of the songs you liked in there, but other songs that are similar enough to it that you get like kind of a uniquely tailored playlist with stuff you like and stuff you haven't heard before. And this is just an algorithm, but people are like, I love the Blush playlist. It always gives me such good recommendation. I find the best music on the Blush playlist. So do the algorithms have personalities? What do they know about us? I don't know, but they can do things. Like they actually do like functional like recommendations work for us. We actually at a point can even start to trust them for what they tell us. So it's kind of like, it's a huge open-ended problem about like what you're assuming, what you're testing, and how to test those things. It's kind of like, it's wide open. There's a lot of room for debate and thought. And so a quick example of a multi-level hypothesis that you could kind of test and implement. Maybe you start out with a hunch, like items are described by hashtags because like either users ascribe them to them or like items self-identify and they're like, ooh, hashtag like clean house and it's a vacuum cleaner or something. And then you have the compute level where you now need to build like a bunch of models that actually use this hashtag data. So you have like this whole kind of like experimentation, like sunk cost debt as an organization, that again, it's important not to take on too early. Like if you have a data scientist and if you give them like maybe like 6 months to just play with models, that could be a bad use of resources compared with like maybe being like, what is the first thing that does the bare minimum? Let's see how it's possible to ship that. Even if it's not user facing, how do we build out the infrastructure to ship it? And then, so yeah, the simplest version doesn't even really need machine learning for a recommender system. At the very least, you could just do like kind of like a most popular, like I've said many times, and I've always maintained heuristics work well, unless the problem's complexity exceeds the ability of the heuristic. And then on serve side, you can kind of design a control and variant in many different ways. But one example is you can test watch-based data recs versus hashtag-based data recs. Or you could try mixing them, because oftentimes like in the industry, people find that ensemble models that kind of combine their logics work really well, and nobody knows why, and at this point it's too late to ask, but we just trust it and we mix them up. And then UI UX again, there's choices here, like should this be shown to everyone, or should we start to get one level granular and say, maybe everyone has a preference of whether this is a carousel that they like or not, and then how do you start to like learn that? Because that's another inference problem that you kind of have to make a bunch of assumptions about, go back into the data and be like, did you click it? Did that mean that you liked it, or that you didn't like it, or that you got bored, or that you clicked it by mistake? And you have to kind of get into that with the numbers and start to unpack those funnels and those kind of pipelines of how people are interacting with your site. And so, yeah, there's so many levels at which you could test this simple hypothesis that, hey, we should use hashtag data. We have a bunch of it, like let's use it to power recommendations, right? So again, just kind of trying to explore this problem out and show you like all of the different levels at which you could possibly think about it or approach it. And then this is really useful. This is something that my team and I laughed about, which is just how do you prioritize experiments? Because you can do everything. You can potentially do everything if you have infinite time and resources. So you really need to only do things that first are easy to implement and test, because there's a lot of you can kind of run into this trap of like, oh, I built this baby and now I want to keep improving it. But you need to also live with the systems that you've built and try to like get the most out of them at the same time. And then on the other hand, of course, you prioritize by impact, and you try to like gauge whether, for instance, the improvement I suggested about the item similarity, I would put like maybe like in the middle here on like ease. But I would say that has a huge impact. And so that's something you would consider as kind of anomalous, because it just like explodes the pool of available recommendations. And that generally is like something that you know is going to be good for your system. It's just going to have way more options. And then anything you build downstream of that could like pare down from those options. But more options in the first place at serve time is usually a good thing. So yeah, this is a bit about recommender systems. There's a bunch of stuff I don't have any time to talk about. We will not talk about scaling compute or scaling serve. We won't talk about testing. We will not talk about A/B testing. They're different things. We will not talk about quality assurance, although we touched a little bit on that. Please show it to a human being. That is all I ask. Recommendations as a product. I'm not a product manager. And then risks, of course. There's like a bunch of risks associated with a machine learning system, both as the organization that is kind of like financially investing in it, but also to like the ecosystem or the economy that you kind of unleash it on. But that's all boring, right? So let's talk about memes. So there's a bunch of good memes about recommender systems. I feel like maybe I can explain some of these, but I hate explaining memes, but yeah, SMM is just social media marketers. So the joke is that every time the Instagram algorithm changes, it's just like a really violent act against all of these people who are really like, think of the way in which people have tuned themselves to the algorithm to maximize their engagement. Like it's kind of wild out here, to the extent where they're like on blogs and on Reddit with each other, and they're like, oh, it changed, and like, oh no, stop gunning for likes now. You ask them to message instead, and they're just kind of like on their own internal little chats about that. Oh, here's one. I mean, just in general, the Instagram algorithm has been noted for being depressing and like, you know, causing body dysmorphia and making teens unhappy and just like being designed to be addictive and stuff like that. So if you're building a recommender system, maybe don't do that. Just a thought. Yeah, this was, I thought, kind of cool, because this is a meme shared by like an independent bookstore, and they're just like, why did you have to go and ask Amazon what to read? Why can't you come talk to us instead? Which I think is kind of cute, because I've enjoyed like conversations with bookstore folks. And then, oh yeah, so here's another thing where it's just like, sometimes you get like this complaint, which I don't know how legitimate it is, but like people will reach out to you and be like, your algorithm has singled me out and like is causing my performance to really drop. And it's like, it's a good question. I mean, I don't know if it is, and that's something that we should actually have a lot more observability on, because when we change like simple things in the data or the code world, like you're just like, maybe we exclude the bottom 50% because they probably all suck, and now like someone's like whole material circumstances are changed by that, right? So it's kind of an important thing to be thoughtful about, I think, while you're making those choices, because it makes you less likely to kind of be blind. You could still make mistakes, but you could fix them. And so, yeah, that brings me down to the biggest bummer part of my talk, which maybe some of you saw coming. But there are ethical concerns with recommender systems. So you don't want to be evil. And some of the easy ways that you can kind of see potential to be evil, that's useful, I think, because then you're like, oh, maybe we try not to do that because we can see it potentially happening. Recommender systems can decide who succeeds and who fails in a digital marketplace. Recommender systems decide what types of content people are shown and how that affects their actions and their thinking sometimes. It can affect what people think they want, and over time, what they actually want, because that's how we work. We're super hacky like that. And that applies to like us as voters, as consumers, the way we perceive ourselves, our body image, and a lot of like murky things like that, especially with social media. And minorities and protected groups are often easily averaged out because their behaviors literally just form like a little mold somewhere, but then en masse, they don't even count, right? Like when you see like what is the meaning of the question, what is the average skin color? What is the meaning of the question, what is the average age? Averages erase information. And so, yeah, there's a little bit of critical reading on the topic if anyone's interested. One of those books is not here. That's this one, Race After Technology. It's really interesting because it kind of just it roots itself very much in how data is being used right now, again by various governments and technology organizations and stuff like that, and kind of thinks about what that is going to, how that is going to change how we perceive like kind of social relationships, people's access to kind of like economic relationships and marketplaces and things like that. And of course, like it's from a race scholar, so she has like a really incisive view into that topic and has like some good calls to action. Also, I would say like the idea of like an algorithmic audit, I think was popularized a little bit by Ruha Benjamin, and it's something that we can all think about, right? We're just like, well, we know that the algorithm exists, it's running its job every day, like can't there be anything that has just like eyes on it if we know that it affects something crucial, like I don't know, anything. And then Zucked, Waking Up to the Facebook Catastrophe by Roger McNamee, that's right over there if anybody wants to take a look. It's kind of an interesting inside look because Roger McNamee was an investor in Facebook and a mentor to Mark Zuckerberg. And then kind of like started to be like, it feels like things aren't going super right here and the priorities aren't super good. And the way that he articulates that is quite interesting, I think, because it just like pushes a lens again into like how you can be super like narrow and horse blinded in like what is possible. But sometimes you miss the effects of that on the real world and you're trying to go so fast that you miss it even more easily. And then the other one is The Technologies of Speculation by Sun Ha Hong, which is also over there if anybody wants to take a look at it. It is kind of more of an anthropology slash like epistemology, which thinks a little bit more abstractly about like how there's a gap between digital representations of things and those actual things, and especially in the case of people, how like, you know, when a company uses a digital representation of a person, there's a gap there. When a government uses that, there's a gap there because people aren't data points. And kind of trying to like probe more into like what that gap is, the nature of it, and how we might like think or do things to address it. And yeah, there's a few things that folks in this room can do to bring more accountability to ML systems. I would say that use your tech literacy for good. I feel like everyone in this room is capable of asking good questions and being skeptical and not taking my word for things, that's for sure. You can organize to define, conduct, and maintain algorithmic audits. Like if there are systems that you notice in like your civic government that are being like algorithmized, you can like ask questions about it because you probably are best equipped to do that. You can encourage best practices like model fact sheets, data reproducibility, and impact assessment, and you can ask questions about these things to people who work in ML. You can educate yourself more about ML, not necessarily like going all statistics and all into the deep dive, but just about like where it's being used, how it affects the world, you know, how governments are using it, how police are using it, how communities are using it, and just keeping an eye on that pulse of the world as it's changing. What the hell is happening on TikTok? I don't know. And then hire and encourage diverse and thoughtful viewpoints on your data teams. Again, it's a really low lift thing, I think, to just have like people thinking or having different viewpoints in the room. It really like avoids blind spots in a lot of ways. And then most importantly, something that Google has no longer thought to include, but don't be evil, because profit at what cost, right? Like, I feel like most of us are here to work on interesting projects and build cool things and give back to our communities, this being one of them. So fingers crossed. All right, thank you for listening and for your patience. Thank you. I'm all yours for questions.
We have a question from the announcements channel. It's a long one, but I'll try to sum it up a little bit. One is, have you tried any other frameworks to serve your on-demand recommender except Flask?
We definitely want to move away from Flask. Like I said, we kind of like wanted I think we had this bias to action, which is again sometimes a bad thing. Mark Zuckerberg did too, but we had a bias to action to ship like the first thing and to see that it would work. We have a lot of problems with Flask, and I think we talked about like Fast API or Django seems like too much, I think, for this use case. So that's kind of where we're at right now. One of the biggest advantages of I think, Fast API, which is what my teammate was telling me, was that we need auto documentation because this API is something that touches other teams. And so Flask is just super janky about it. And yeah, we would really like something that can like auto document and have something ready for other teams to reference that updates by itself.
What other questions? Okay, one second.
No worries. So, like you said, like this could have like infinite. You can do it like to the infinite point. When you're working with any of them, do you have like a timeline as a goal, like increase in percentage of clicks? Like, what will be like? Of course, there's no right or wrong answer. It could be project dependent, and I'm not sure if you can share. But what will be like your go-to? Okay, this is good enough. Let's work on a different project. You know.
I think that's a really good question. And again, I would say that the answer to that is really different from organization to organization. And it is something that like data people should never decide. Like it is something that someone with a pulse on the organization should kind of be looking at the numbers and being like, is this actually improving? For instance, like just as an example, like you could have like a site that, you could have different sites that both count watch time, but like maybe watch time is not the most important kind of metric for the specific niches that those different sites serve. Like maybe it is for one of them, but maybe for another, it's something like followers or comments or something else, right? So it starts to become kind of a thing of you need to make sure that you need to make sure that the user experience is mapped to, in some sense, like, you know, you start from first principles and be like, what makes this better? And then think about how to measure that in data. Another, I don't remember what the name of this thing is, maybe it's Goodman's paradox, but it's kind of like a thing of like, if you, the more you try to optimize a metric, the less meaningful the metric becomes, right? So I may be really horribly paraphrasing that, but hopefully that kind of carries. Yeah.
Another question.
Yeah, I wonder if you could speak to sort of like how you might consider uncertainty in your model. So you have a score for how much you think a person likes something, but maybe you may be more confident about certain relationships than others. And I think the way that like this may contact a product is that like a Discover Weekly on Spotify, like the goal there is not to just recommend songs they think you'll like, it's songs that you haven't heard yet, or artists you haven't heard yet. They're going to take a few more flyers on stuff that may not hit in order to do that. So I'm wondering if you use that at all in your work, what are your thoughts on that?
That's also a really good question. I think again here, this is the part where you need to think about the last mile of the service, because if you brand something as Discover Weekly, people know what to expect. But if you call it old hits, they're going to be like, what is going on, right? So in a weirdly interesting way, as you build this family of recommenders, you want to give, like, not give as much as you want to be receptive to signals from your user base about which of those they actually liked. So that you can like give them the best buffet, because you have the catalog accessible at any point. You're trying to kind of like learn these preferences of even individual recommenders. I think that kind of characterizes it for me. I feel like you could try different things that could work for some users, that the same thing just doesn't work for others. And that is also a point that you want to be able to reach, where you're like, I actually know this now. That would kind of signal an advancement of how you're running your machine learning pipelines.
Oh, okay. Phil, come first.
Hi there. Wanted to go back to your architecture. You said you had something you were using in place of Airflow, Dagster or Dragster. Could
That's
you talk about what that is for a minute?
Sure. So let's go back. Wow. Okay. So Dagster is basically what runs and orchestrates in this little box here. I think if anyone is familiar with Airflow, or I think Prefect is considered another alternative, but Prefect is not open source. So it's kind of, you have to pay for it, each membership or whatever. And then Airflow is, I think, Apache's or something like that. And what it allowed you to do was kind of like connect executions with and sequence them with dependencies on each other. But I have not actually used it as much because of the amount of crap that I saw I got on Twitter. So I read a lot about Dagster, and what I can speak to is Dagster and what I like about it. I think like the ability to kind of like sequence everything into a DAG that you can see on a user interface is really useful for machine learning engineering, because I literally have steps that are labeled like, okay, report configuration, like read the SQL query as like txt from a SQL file, execute that SQL query on our database, build the matrix, factorize the matrix, and then kind of like spread out into like this distributed job. And I can kind of see all of that in a pretty user interface that is also like really neatly composed out of software pieces that I just put like little wrappers on top of other functions, and kind of like I'm able to compose this whole operation. And then the other thing that Dagster lets you do is use the UI to actually schedule these jobs. So especially if you're kind of like a younger organization and like you maybe don't have a lot of experience and you really need to have like the ability to go in and really change things or keep your eye on things, I would say that Dagster is a really useful tool, because you can go and see like the history of all of the jobs. There's like queryable database. It's maintained, I think, in SQLite, but you can easily port it to Postgres or any cloud database that kind of maintains like information relevant to all of your runs. And just kind of a lot of neat things that I think people have also used Airflow for, but then sometimes you don't get all packaged in one location. And one of the critiques I have heard about Airflow is that it does not have kind of like cross-job awareness or visibility. I don't know if I'm representing this right, but in Dagster, it's actually really easy to kind of like save state as you're going through this pipeline, and to kind of catch, and like something breaks and you just kind of click on the previous step and rerun from there, or you can do that in the with the command line as well. But the user interface is actually, I would say, a good sell for Dagster. It's really pretty, it's intuitive, it's easy to use. And Dagster was built by someone who was originally at Facebook, Nick Schrock, and then he left because he was like, I think that there's a better way to do data pipelines, and I'm going to build it. And he has definitely a bit of a different approach than what I've seen in some of the other tools available. Yeah. I will say it's a little tricky to start with, though, because it is a young tool, so the documentation is a bit young. But they recently put out their first stable version, the 1.0. Actually, today my job was to migrate to 1.0. It was really boring.
You did it in one day, so.
Yeah, so when you roll out your new model, you actually can influence user behavior, and you can have like this infinite loop where you recommend a bad product and users click on that because it's just recommended. So I don't know if you have any thoughts on how to correct for that.
I think so. So there's one thing though, which is that you can trust your users. Like the chances that they will click on a bad product are really low. But the chances that they will not click anything, or that they'll just be like, what is up with this site today, and never come back, those are really high. So in some sense, like you have to advance your internal quality assurance to the point where you know that that's not going to happen. One simple way that we did that was we built out like the serving infrastructure, and then we just put that on like a staging server that was not live, and we just had like a bunch of like product people and like just people who are kind of familiar with the site, just kind of use it for a bit and actually just use it. And we found a ton of like little things that we could tweak there. We found a ton of like kind of structural engineering little bugs that were making things go wrong. Again, like I was the first machine learning engineer, so a lot of this infrastructure is being built for the first time. Teams are learning how to kind of deal with these new pipelines for the first time. But yeah, there's kind of like a lot going on that you can kind of like focus on at each different level.
But like the problem could be more subtle than the example that I showed. Like, do you at all like control for data that you logged after you rolled in your system and data before, or like between different versions, or you assume that like this doesn't change a lot of, you don't have to adjust for that?
Oh, I think okay. One thing that I caught on that you mentioned is yes, we definitely want to like close the loop and be like, which of the recommendations that we showed were actually engaged with. And like I said, what is your model doing? Right now we're doing candidate generation. There's steps that you can do downstream, like filtering, rescoring, and stuff like that. Imagine a rescoring model that is trained just on like the last mile stuff, like what people were shown and what they actually clicked, right? Like that would start to pick up some real nuanced preferences about things. And you could kind of, again, stack them up. You could have different stacks. So now again, the notion of like a graph of operations, which has like, different types of branches and trees growing in space, again, starts to make a little bit more sense. And Dagster allows you, DAG stands for directed acyclic graph in Dagster, right? So it allows you to kind of compose your graph of operations in a pretty intuitive way. Yeah.
Thank you.
Any more questions? So.
Back to the topic of risk, it's a simple intuition assumption, please correct it. What I understand with recommendation engines, recommender engines, and just generally a lot of social media and technology is engagement drives a lot of business decisions, it drives a lot of technology decisions. If that assumption is correct, then to go back to the topic of risk, does that mean that your risk tolerances in your company, and just speaking generally from what you understand, is that you are less risk averse when rolling out a hypothesis, testing a hypothesis, even asking your business analyst to review certain output from some hypothesis? Do you find that the engagement results in more risk averse behavior?
I think that's a really good question. And again, it's important to think about that when you're kind of trying to strategize your own project. I would say that I don't think that my situation is as descriptive of risk, because it's kind of the converse, that they were at a stage where they realized that a recommender system was a much needed investment, right? So when you're at that stage, it kind of isn't a risk as much as you're investing in this piece of infrastructure. Now, maybe the infrastructure will do a crappy job for a bit, and then you just keep it kind of at like 1% traffic until you fix it. And that's kind of the stage that we've been at for the last month. And now we're kind of like ramping up traffic. We went from like 1%, 5%, 50%. And eventually like recommendations on the site on the whole will be served by this system. Then we move towards like a live system, like I talked about, so that we can have like this diversity of things and move more towards experimentation to figure out what configurations are good and try to find more granular preferences. So I would say that like in terms of risk, like there effectively wasn't as much risk here because it was an asset that is just extremely sensible for this business. And some of the ways you could identify that are if your business has a huge catalog, obviously. Because that's kind of why I prefaced with the discussion there, because a recommender system for like a cafe is probably not a good idea, right? Like it's not a sensible investment. You would probably maybe want to use some out of the box like Google recommendations or whatever Amazon's thing is called or whatever for those types of smaller applications. And I mean, there's kind of right ground there to kind of modularize and speed up setup for small businesses. But it's not something that is worth like hiring a team, setting it up and expecting it to be on the runway for like 1-2 years. It only really makes sense if you know that your business problem is that of a massive marketplace with many, many items that you know that your users have certainly missed connections with items that they would have liked. So, something like Etsy, eBay, obviously any content website, any streaming website, stuff like that. Those are cases where it would be extremely, extremely useful. Target or whatever, yeah.
Last question.
Thanks a lot. Going back to that one point you had about the simplified model, the toy model, where would you start with? What types of algorithms would you start building your own recommender system by hand? Before you start dreaming up ML pipelines and things like that.
Great question. I mean, one thing you can do without any machine learning is just set up a recommender system that serves up most popular, right? Like, so you don't have you just set up all of the infrastructure to maintain a list of who's available with some type of updated ranking. So you set up a cron job to update the ranking, and you set up a serving infrastructure to just retrieve most popular at any time. And that actually works pretty well for a lot of sites. I mean, for most restaurants or cafes, you literally just see that it's just at the top, it's just this is what the most people have It's literally just the mode of the distribution, 5 items up there, and if not, you can scroll all the way down. And that works actually really, really well for many, many use cases. In fact, it's sufficient. You can stop there for a bunch of different use cases. Does that answer your question? Is there any?
Let's give our speaker a round of applause. Yeah, thank you very much for that. It was really cool.
Thanks, folks.
Everyone, that's ChiPy. Thanks for coming tonight. There's more pizza back there and drinks, I assume. So thanks for stopping by, and see you next month.